In this video, we will learn about the transition metals, some of their uses, and their chemical and physical properties. Before we look at this very interesting collection of elements, it's important to know which are and are not included. The term transition metal is about 100 years old. It originally meant any element that sits between groups 1 and 2 and groups 13 to 18. These elements provided a transition between the two blocks, although it should be noted that not all of these elements had been discovered at the time. Today, this definition would include all of the D block elements and all of the F block elements as well. However, over time, certain properties of this collection of elements have become signatures and certain elements were removed. For some elements, there is disagreement over whether they should be called transition elements. I won't go into the details of these disagreements, but I will show you which elements are generally considered transition elements. The definition from the International Union of Pure and Applied Chemistry, IUPAC, includes these elements. Almost universally, zinc is not included. The status of cadmium and mercury is hotly debated, and for some of the heavier elements, there hasn't been enough experimental data to make a clear decision. But in practice, elements in group 12 of the periodic table are not considered transition elements. At the other end, some people don't consider group 3 elements transition elements either. This includes scandium and yttrium. To keep things simple, in this video, these are the elements we will consider to be transition elements or transition metals. This means we're including any element in group 3 to 11 plus any element in the F block. Another thing that happens in practice is that transition metal generally refers to only those transition metals in groups 3 to 12, and those in the F block are specifically referred to as the inner transition metals. Meaning that what we're left with when we talk about transition metals or elements are the elements in groups 3 to 11. This is the collection of elements we'll be considering in the rest of this video. We won't be looking at the reasons for the properties, just the properties themselves. Next up, the physical properties of the transition metals. Like other metals in their pure form, transition metals are thermally and electrically conductive. However, the three most conductive metals of all are all transition metals: gold, copper, and silver, with silver being twice as conductive as aluminum. The transition metals are also generally quite hard, at least harder than the main group elements like tin and lead. Some of them are also very strong, like iron and titanium. The mass of 1 cubic centimetre of water is about 1 gram, so water has a density of 1 gram per cubic centimetre. The element lead in metallic form is generally considered to be pretty dense, being 11 times denser than water. But the densest of all the elements are osmium and iridium, which are 23 times as dense as water and twice as dense as lead. And there are actually 10 more transition metals in the D block that are denser than lead. Like many other metals, transition metals tend to be malleable and can be hammered or rolled into various shapes. And they're ductile, so they can be drawn into thin wires. And they're shiny like other metals or lustrous and can be polished to a mirror finish. Last of all, transition metals tend to have high melting points. Lead, in group 14, has a melting point of about 328 degrees Celsius. But the metal that has the highest melting point of all the metals is tungsten, a transition metal. Now that we've looked at the physical properties of the transition elements in their metallic form, let's have a look at their chemistry. One of the most important distinguishing features of transition elements is the number of compounds they can form. A lot of this has to do with the fact that they can form different stable ions and oxidation states. Main group metals like magnesium and aluminum tend to have only one common oxidation state. Magnesium tends to form Mg2+ ions, while aluminum tends to form Al3+ ions. But we can see many other stable oxidation states for some of the transition metals. Here we're going to go through the first row of the D block. Scandium is an exception in that we only tend to see it in the +3 oxidation state, neglecting 0 of course. The other transition elements along this row have multiple common oxidation states. For reference, zinc, at the end of this line of the D block, has only one common oxidation state, +2. It is important, however, to remember that sometimes we can get different oxidation states than these. These represent the common oxidation states, and some people disagree about exactly what common is. Therefore, you should only take these numbers as guidance. When we find transition elements in low oxidation states, we'll typically see them as ions, whereas the higher oxidation states we'll typically see as oxides or fluorides and so forth. As an example, we can see the great variety of compounds possible with manganese, with all these possible oxidation states. The ability to easily switch between these available oxidation states allows for a huge range of catalytic and electrochemical behavior. The other striking feature of transition elements is the variety of colors of their compounds. If we look at the color, we can predict what frequencies of light the ion is absorbing. For instance, an ion that absorbs red light looks green. Ions of zinc, magnesium and aluminum have no color whatsoever. Scandium 3+ is also colorless. But solutions of titanium 3+ are purple. There's quite a variety of vanadium ions or vanadium oxide ions with color. Solutions of V2+ are a violet purple, while solutions of V3+ are green. Solutions of VO2+ are blue, and solutions of VO3+ are yellow. Solutions of chromium 3+ are also a violet purple. Manganese can form a huge variety of coloured compounds, but I'm only going to include those you'll probably come across in solution. The Mn2+ ion makes solutions a pale pink, while solutions of the permanganate ion, MnO4-, are an intense purple. The most common ions of iron are Fe2+ and Fe3+. You may see the colours of Fe2+ and Fe3+ quoted differently because it does change depending on the environment. But generally speaking, Fe2+ solutions are green, while solutions of Fe3+ are yellow or brown. Solutions of cobalt 2+ ions are generally pink, but they can turn blue if extra Cl- is added. Meanwhile, solutions of nickel 2+ are green, and solutions of copper 2+ are generally blue. These colours are not exact. The counterion and the environment, the temperature and so forth can affect the colour of a transition element ion solution. However, in certain controlled environments, the colour can be so distinctive we can use it to identify the ion. Now we can move on to one of the more unfortunate properties of some of the transition metals, toxicity. Before going any further, it's vital to point out that toxicity depends on the form of the element, whether it's pure form or whether it's in some kind of compound. Some of the transition metals form compounds that do vital jobs in plants and animals. But for some of the transition elements, like vanadium, chromium and cobalt, very many of the compounds are highly toxic. But as with many materials, many of the transition elements in high doses will be toxic, including those that are vital for biological functions. The last significant property of the transition elements we need to look at is reactivity. In their pure form, none of the transition metals are highly reactive. And in fact, the least reactive metals of all are transition metals. Silver is quite unreactive, but will tarnish. Gold, however, is considered to be the least reactive metal of all. A good test of reactivity is how a metal responds to acid. Copper is more reactive than gold and silver, but it will not react with acids on their own, so it's considered relatively unreactive. But the majority of transition metals do react with acids. Also, most of the transition metals will react with oxygen, forming transition metal oxides, although some, like copper, need to be heated first to get a decent reaction rate. On the other hand, the transition metals generally at room temperature will not react with water. The process of iron rusting is a separate type of process. But with enough heat, some of the transition metals will react with hot water or steam. In compound form, the transition elements can be oxidized and reduced, switching between those available oxidation states. For instance, we can oxidize Fe3+ to Fe2+, or reduce Fe2+ to Fe3+, switching between green and yellow/brown forms of iron ions. This behavior is partly what contributes to transition elements and transition element compounds being fabulous catalysts. For instance, iron is used in the Haber process to convert nitrogen and hydrogen gases into ammonia. And vanadium 5 oxide is used as a catalyst in one of the steps of the contact process, helping to convert SO2 into SO3. And there are many biological molecules that depend on transition metal ions in order to function, like enzymes and proteins. But it's all very well looking at these things in isolation, but we'll get a better idea of how transition metals fit into the greater picture by comparing them. Let's compare the first transition series, the top row of the transition metals, with the group 1 and group 2 metals in the same period, and I'll also throw in zinc. All these elements in their pure form are lustrous, and most are silvery, and copper is an orange-brown. All of these transition metals and zinc are relatively hard, but potassium and calcium are quite soft. Something really interesting pops out when we look at the melting points. Here I'm presenting them in Kelvin. Potassium has a relatively low melting point at only 337 Kelvin. Calcium's seems much higher. Potassium's melting point is only 64 degrees Celsius. But the melting point for all these transition elements are all substantially above 1300 degrees Kelvin. And we see the melting point drop down again at zinc, with a melting point of only 693 Kelvin. The differences between the alkali and alkaline earth metals become even more dramatic when we look at their chemical properties. When potassium or calcium are added to cold water, we see fast, almost explosive reactions. However, none of the transition metals or zinc react directly with cold water. The rusting of iron is a separate process. Meanwhile, pure calcium and potassium will react fast with oxygen, tarnishing in air. But for the rest of the elements, the reaction is slow and generally requires heat. But the most dramatic difference occurs when we use acid. Potassium and calcium explode, while the transition metals have slow reactions or nothing at all in the case of copper. And if we look at the number of common oxidation states, the average for the transition metals is significantly higher for the alkali or alkaline earth metals. And we can also see that the alkali and alkaline earth metals are significantly more reactive overall than the transition metals. After all that, I think it's time for some practice. Which of the following is not a transition metal? A. Gold, B. Cobalt, C. Potassium, D. Rhodium, or E. Zirconium. Transition metals are otherwise known as transition elements. And where do we find elements? On the periodic table. The periodic table of elements condenses lots of different bits of information about the elements, so we can see it all collectively. The elements inside the green area are generally known as transition metals, and the ones most people talk about are in groups 3 to 11 of the periodic table. Now, let's see which of the elements listed actually lie inside the area. If you look carefully, you'll find the entry for gold in group 11 and period 6. The symbol for gold is Au. Cobalt, with symbol Co, can be found in group 9 and period 4. Potassium, with symbol K, is also in period 4, but it's in group 1. Rhodium, symbol Rh, is found below cobalt in group 9 and in period 5. And lastly, zirconium can be found in group 4 and period 5. We can clear away the F block because none of the elements are inside it. The only element that's not inside the area is potassium. It is not a transition metal. Potassium is in fact reactive, soft, and an alkali metal. Therefore, out of the 5 elements, the only one that's not a transition metal is potassium. Now let's have a look at the key points. Transition metals or elements are found in the D block and F block of the periodic table. Those in the F block are generally known as inner transition metals and won't be included when we talk generally about transition metals. Like many other metals, transition metals are electrically and thermally conductive and lustrous or shiny in their pure form. They are also strong and hard, malleable and ductile, with high melting points. They tend to form coloured compounds and commonly have multiple common oxidation states, which is part of why they can be very good catalysts. They are also less reactive than alkali and alkaline earth metals, and the least reactive of all metals are transition metals.